Hello, everyone. So thanks for coming to the talk. In this section, we are going to talk about the challenge of doing machine learning in Samsara, specifically how we build a machine learning platform to overcome some of these challenges. So my name is Peng. I'm the tech lead of Samsara's machine learning infrastructure team. And please also allow me to introduce my colleague, Shurab and Sharan. So Shurab is a senior machine learning engineer in our machine learning infrastructure team as well. So he builds the workflow orchestration framework in the platform. So he will cover that in this presentation. And Sharan is one of our early members in the Samsara's computer vision team. He developed many of Samsara's AI features in the early stage of the company. He will cover a model optimization use case with Samsara's IoT device in the loop in the last part of this presentation. All right, let's talk about the company. So what is Samsara? Samsara is the pioneer of the connected operation cloud. So we are digitizing the world of physical operation. So think everything from energy, utility, food delivery to transportation and warehousing. Our platform makes our customer easy to act on IoT data from locations like warehouse, trucks, and heavy equipment, which ultimately will help them run safer, more efficient, and more sustainable operations. So now we know the company, let's talk about the challenge of doing machine learning in Samsara, which is establishing the data flywheel. And that challenge actually comes from a combination of three aspects. So the resource constraint on the edge, the data imbalance due to the nature of the problem we are trying to tackle, and the scale required to process unstructured sensor data. So first of all, let's talk about resource constraint. So all Samsara's data coming from the IoT devices we built. And many people think like resource constraint on IoT device only impact machine learning inference because it has limited capacity, but they overlook its impact on data collection. Because while dealing with constraint on inference, maybe it's a problem, an optimization problem we can deal in a later stage of machine learning project. But if we are not being able to collect data, the machine learning project could be killed in the early ideation stage. So one such example is in our AI dashcam. We can't really stream all the data to the cloud due to the cost of maintaining a reliable cellular connection. And another example is if we wake up the device too frequently to just for the sake of upload the data, it can kill the battery, or it can drain the vehicle's battery that the device plugs in. And nobody wants to see that battery in their car. So the second challenge comes from the feature we are trying to develop. So many of our products are targeted at detecting unsafe operation behavior, like distracted driving or tailgating. And these events are rare in life and difficult to collect by itself. So the third challenge is coming from the scale of processing unstructured sensor data. So given the first two challenges, to get enough data points to bootstrap our project, one common technique we usually use is analyze multiple streams of sensor data. And maybe at that stage, we run some machine learning model to detect the interesting data point and then join them together to figure out the interesting interval we want to either use the data point or further request any more data point. And such a process actually requires to build a large scale and also very complex data processing pipeline. All right, so then how Ray help? This is Ray Summit. We got to talk something about Ray. So the first thing we are excited about Ray is obviously its capability to scale. So with Ray, we can scale our experiment to hundreds of millions of input images with the code that originally developed and tested on the laptop. And another thing we like Ray is its ability to improve a complex workflow, or in another word called AI productivity. So this is something I learned actually today earlier from our keynote. So as everybody knows, machine learning development is not just about training the models, right? So data processing, hardware in the loop optimization, and also offline and online evaluation, also online inference is also an integral part of our machine learning lifecycle. Without Ray's ecosystem, this process would have to be implemented through multiple platforms, which requires significant work to build and integrate. And also the scientists, when they work on this project, they have to hop through multiple platforms to finish some simple task. And this is a high-level architecture that of our machine learning platform and the machine learning stages it support. So the boxes in the upper part, I'm not sure if you guys can read it, is the machine learning lifecycle stages. And the boxes in the lower side are the tools we use. And especially the blue boxes here is the place we use Ray. As one may already see, so we use Ray across the board. So in some cases, like data processing, Ray is used as a compute orchestration framework supporting the actual processing engine like Apache Spark. We will cover later on how we do that in the presentation. And on other ML-focused areas like model training, Ray is directly used as the API and computation framework. And for online inference, my colleague Brian would cover that in another talk around 5:15 p.m. today, and I encourage everybody to go and check it out. So in the following section, we will deep dive into use case how Ray is used in our platform. So first thing first, data processing. So Ray itself comes with a pretty good data processing capability. However, sometimes we still need, we figure out ourselves, we still need more in our setup because the need to join, while doing the feature extraction on processing sensor. Unfortunately, there are many ways to do that using Ray's ecosystem. So in our way, we choose to run Spark on Ray because it's easier to integrate with the remaining data stack in Samsara. So Spark on Ray is actually enabled by a library called RayDP, which is developed and open source by Intel. The idea behind RayDP is pretty simple. It combines Spark and Ray cluster, so we can do data processing and later on training in one Python script. And using this project is pretty straightforward. As you can see here, you just do pip install RayDP, and then connect to the Ray cluster, which is pretty standard. And then call RayDP init Spark and feed the Spark parameter into the function, and then you get back the Spark section. So once you get back the Spark section, everything follows naturally. So I just take the NYC taxi example from the RayDP project for the sake of demo. As you can see here, it first ingests the data by loading a CSV file. But in your environment, you can totally read the data from the data lake, whatever place you want. And then once you get the data frame, you just do whatever data processing you want. And then you can convert that Spark data frame to Ray dataset, and then further feed into the training framework that Ray provides. So how does it work under the hood? So under the hood, all the Spark executor and driver are scheduled as the actor, as a Ray actor, and scheduled by Ray. And all these things are taken care of by RayDP, the library RayDP. However, with this setup, there is one glitch. So Spark has this concept of driver and executor, which the driver actually maintains the cluster. However, when you schedule the driver actor on Ray, Ray doesn't have this knowledge. So your driver actor can land on a spot machine, which can get terminated at any time. So when the driver dies, basically your job is died and it's not recoverable. So to overcome this problem, we make a contribution to the RayDP project, which is the idea is we allow the developer to specify where Ray should schedule the driver and executor using the custom resource annotation. So as you can see here, so first of all, before we launch in the Ray cluster, we let the user to define custom resource on the different machine types. So in this case, we say one type of machine is Spark master, one type of machine has custom resource, Spark executor. And then when launching the Spark job, we use two RayDP configuration to basically tell Ray, hey, for Spark master or for the driver actor, please put them on the machine that with the Spark master annotation. And optionally, you can also tell RayDP to put Spark executor into the executor machine. And also another trick you can make here is, as you can see, the Spark executor actually occupies one resource. In fact, you can also specify, like say, Spark executor actor.resource.cpu to a fraction of the CPU resource, so to achieve CPU oversubscription, because CPU also work as a regular resource in this case. All right, so that's it for data processing. So I would turn the presentation to Shalab to talk about our machine learning workflow.
Awesome. Thanks, Wang. My name is Saurabh. I'm a senior machine learning engineer at Samsara. And I'm going to walk you through how we build or develop the orchestration platform at Samsara. So when we started building it out, we had key requirements in our mind. We wanted to keep track of the data lineage as well as the code lineage. We wanted to support local development and debugging. We wanted to make sure there's dependency isolation between the pipelines. We wanted to have the orchestration system be container native. And we wanted to also have like an easy-to-use GUI. So then we started evaluating all the available orchestration frameworks on these parameters. And the one that stood out was Dagster. Dagster is an open source orchestration system. It's really feature rich. It's developed by the Elemental team. And if you guys haven't checked it out already, I'd encourage you to go and check it out. So Dagster was the chosen orchestration engine for us. And we started onboarding pipelines on top of Dagster. And that's where we basically got the first gotcha, which was even though Dagster is like really easy to use and it has a very good set of documentation, but there's still a bit of a learning curve, and it just sounded counterintuitive to us. Like, why should a scientist be required to learn a new technology if he has to, basically set up a workflow? And that's where the whole concept of this declarative workflow definition came in. So the idea is that the scientist should just be able to tell us that, okay, as part of this pipeline, I need to run these tasks, and I need to run this at this particular cadence, and that should be about it. And that was basically the genesis of Owlster. Owlster is a Python wrapper which works on top of Dagster. And what it does is it offers a YAML-based interface for the scientist to basically specify his pipeline without using any code. It also comes in with, it also supports one-click deploy. It also supports out-of-the-box alerting and monitoring. But the main use case is that you can define your pipeline completely in YAML without any code. So now let's look at what an Owlster config looks like, what the YAML file looks like. It majorly has 3 sections. First is the alerts. The alert section basically tells you who do you want to alert and how do you want to alert in case, or basically the status of your job. The second is the schedule section, which basically tells you what is the cadence with which you want to run the job. You can also specify the time zone in which you want to run the job. And the third is the ops section. This is the real meat of it. This is where the scientist defines what all are the tasks that he needs to run as part of the pipeline. So let's look closely on the ops section. On the left-hand side, you see the ops template. It basically has every entry in here is essentially a task, and each task essentially maps to a Python function. So start array cluster and the array execute function. Start array cluster essentially maps to a Python function which will start array cluster for you. The array execute maps to a Python function which will execute a command on the array cluster. And then again, your pipeline can have multiple array clusters. You can have multiple commands that you want to execute on it. So you make use of aliases to uniquely identify which task corresponds to which Python function. All right. So the first thing that we need to do is build a dependency graph, the thing that you see on your right-hand side. How we do it. As I said, everything like array execute, it maps to a Python function. So it will have some input, it will perform some logic, and spit out some output. So the key idea here is that as long as I'm able to map output of a function with an input of this array execute function, I'd be able to set up this dependency graph or this DAG. So in this particular case, cluster IP is an input, and it knows that it needs to get it from this dataset publishing cluster, so it knows it needs to execute it before it executes generate training data. Then we look at the execute command, and we see we need to get the start date and end date from this get run dates function, so it knows it needs to run get run date before it executes the generate training data. And this is how basically we set up this dependency graph. Now, there could be a case where there's no explicit dependency passing between the two functions. So in case of publish data set and generate training data, there's no explicit parameter that is being passed. But you can use this upstream command and say that, okay, you know what, just make sure that you run this generate training data before you run the publish data set. So this is pretty much how we set up this particular DAG or the dependency graph. Now let's look at the ops. Now, we already said that ops is essentially maps to a Python function. So based on how these Python functions are defined, we classify ops as on-the-fly ops or predefined ops. Let's look at the on-the-fly ops. On-the-fly ops are the ops for which the Python function is not predefined. It is something which gets generated on the fly. So we consume this template, and we create a Python function for this particular task on the fly. How we do it is we basically look at this execute command. We see that, oh, it needs this output table argument. And how do we get the output table argument? We need to combine this database and table name to get this thing function. We look at the filter argument and see we need to get this started and then date from this get run dates function in order to compose this filter argument. So based on this, we create a Python function which essentially takes these 4 inputs, and in the logic part of it, we basically make sure that we are able to concatenate these inputs in the way it's defined in the template, and we execute basically this particular job on array cluster. All right. I just wanted to highlight, like, if you see like the flexibility with which you can define the arguments and flexibility with which you can use it, it kind of shows like, okay, this platform, how capable this platform is. The next set of ops are the predefined ones. Here, the Python definition is predefined, so you don't really have to worry about parsing or basically writing the signature of the function or writing the logic of the function, but it poses a different kind of a challenge. The challenge is, if you look at this input parameter batch name, it's one input, but what it does, it essentially takes outputs from 3 different places and combines it in an arbitrary fashion. So in order to overcome that, we basically make use of wrappers and hooks to make sure that we still support this functionality. Now, it might look like a little redundant of specifying batch name like this, but if you just think about like how we defined filters in the last function, in the last slide, you can see the amount of flexibility it offers for you to define a predefined function, as well as the flexibility in which you can use it. So now, to wrap it up, I'll just gonna showcase the entire workflow, how Dagster and Dagster basically work with each other and provide this seamless experience to the scientists. So it all begins with the YAML file, the config with the scientist defines. Dagster package basically consumes it, it parses the template, it builds a dependency graph, it generates all the on-the-fly ops, and what it does, it passes this Python function and the dependency graph to Dagster. Then Dagster does its magic, it sets everything up, creates a great UI, and makes sure all the jobs are run at the right time. It also takes care of passing the parameters between the functions. And the next stage, when we have the parameters, also kicks in again, and it makes sure we're able to combine these inputs in the way it's defined in the template. It also takes care of launching and running array jobs, managing the array cluster. And once the job succeeds, Dagster is responsible for alerting, logging, and monitoring. All right, so this is pretty much how we build a completely no-code YAML-based workflow solution, orchestration solution for Samsara. Next, I'll let Sharon walk us through a model optimization use case.
Okay. Thanks, Saurabh. Hi, everyone. So as Pang and Saurabh mentioned, Ray has been really pivotal to Samsara and how we build our CV applications. Given all the foundational aspects that they've spoken about, I wanted to spend a little bit of time speaking through one of the applications where Ray has helped us enormously. In specific, given that Samsara really wants to advance towards building a connected operations cloud, I wanted to speak a little bit to something unique that blends Ray and Samsara together, which is about how we do hyperparameter tuning with device in the loop. So when we think of Samsara, the first thing that comes for a computer vision engineer is the dash cam. The dash cam is nothing but a camera that's mounted on our devices. It's mostly dual facing, pointing towards the road and towards the driver, and it helps us advance our mission to improve driver safety. So it looks at the road and tries to identify risky driving behavior, looks at the driver, trying to make sure that the driver is alert and improve their quality of driving overall. These cameras are mounted on thousands of vehicles that run every day on the road, and they power all these CV applications that we're speaking about. Needless to say, they're mission critical when it comes to driving safety for us. All our computer vision applications that we build are deployed on the camera. Very few of them live outside, but the primary ones that govern safety live, breathe, and operate on the camera themselves. And when we think of models that are operating on the edge, immediately the things that come to mind are the characteristics that define these processes. So when we think of computer vision applications on our dash cam, we know that these applications don't have the same leeway as they would on traditional cloud platforms. They have to run on power-constrained environments. They have to pay heed to anything related to thermals and memory. Thermals has been a plague, a bane in our arsenal forever, to making sure that devices don't get overheated when we run our models. We can't throw the biggest, baddest model out there into the camera, and we really have to be mindful about what we put in and the various changes that we need to make sure that these models run on the camera. End of the day, any application that we build needs to be profiled to understand how they run on the camera versus how they would traditionally on the cloud. We need to optimize it so that they run on the camera better and not just optimize it for the cloud and hope that they would run on the camera. And eventually, we also need to monitor these on the field so we know that they're performing as we hope. All in all, we needed a system that helps us build, deploy, maintain, and observe these models on device rather than elsewhere. So back in the early days of Samsara, models were a lot simpler, processes were a lot more fluid. The company was definitely smaller. We could definitely patch together a bunch of work to make sure that models, data, processes could run on the camera, and they ran fine. But everything is meant to break at some point, and as life goes, some things are just good from far, but far from good. So eventually, things break. And for a hyper-growth company like Samsara, when scale hits us, having these patchworks doesn't help. And that's where Ray came in to help us. Before we get into that, I wanted to point out what the specific challenges were when we went through this journey of moving from low scale to high scale, and in a very short span of time, nearly 2 years. When we think of pushing models onto the device, these models have to live on multiple thousands of devices, and they need to live on those devices almost asynchronously. So models, data, and anything related to pipeline and orchestration needs to be moved from wherever they're defined to the device where you want to run them, profile them, and observe them. When we do this, and when we think of devices, the same runtime selection challenges are persistent there as well. So we need to understand whether we want to run them on a CPU, which is fairly accurate but low, GPU, which are just power-hungry monsters when we think of them on edge devices, or DSPs, which are far less detrimental to power and thermals, but are far less accurate when we think of quantized models. These models also need to be running within elastic processes so that we can scale them from 2 devices to 20,000 devices at the same time. And while scaling, we also need to make sure that they're very fault tolerant. We don't want one trial failing somewhere affecting everything else. We want to make sure that all our processes are well monitored, versioned, and anytime there's a failure, we know we want to pick back up wherever we left off. And to do all this from doing scripts meant we really wanted something out of the box so that we could focus on the product and rather than the process of how we do this. And that's where Ray really came in and helped us. In this slide, I'd like to talk a little bit about a high-level view of the architecture of how we use Ray to do hyperparameter tuning on the device. So as with any Ray system, we have a head node that defines what trials we want to launch, and we have worker pods. The only difference between our worker pods and something more traditional that will run on Ray would be that our worker pods are linked to cameras. These cameras are where the models run. So when we think of hyperparameter tuning, we have a bunch of experiments, trials that we want to run and fan out across cameras. The head node makes sure to reserve and schedule these processes on worker nodes. The worker nodes accept the model, accept the data, do all the conversion that's required to run these models on device. So this would be anything to do with like quantization of these models to make sure they're runnable on the SoCs of our choice, to prune these models, to make sure the layers and the pipeline parameters are defined well, and make sure to transport and accept inferences from the camera where they eventually run. All this requires a bunch of orchestration, and Ray really makes it really simple. Some of the out-of-the-box solutions that Ray offers just makes running jobs at scale extremely simple, helps broadcast these models to devices in a very flexible manner. It has a bunch of scheduling algorithms, PBT, if some of you have used it, to really do this whole multi-arm bandit of explore and exploit which models we want to choose how and when, and really prune these models as we go along, because cost is something that's relevant when we think of edge devices and running models on the edge. Finally, when we run these trials, we also want to make sure that we version them, store our checkpoints, and restore these checkpoints when they fail. Some inbuilt trial mitigation and auto-scaling features that Ray offers also really helps us do this hyperparameter search at scale and in almost a mindless fashion. One example of what this looks like is given here in this pseudocode. It relates to quantization. All models, when we run them on devices, by and large, we want to run them on our signal processor, which accepts quantized models, 8 or 16 bits. And quantization itself is a science, and it has many parameters associated with it. Cross-layer equalization, bias correction, you can name a bunch. How much do we want to quantize, which layers do you want to prune, et cetera. And when you build a model, you don't know which of these are right and wrong, and which of these specifically will play well with the hardware. So defining these within the landscape of rate tuned and letting them loose on our cameras really, and asking Tune to optimize for the right set of parameters goes a long way in finding which the best performing setup is without putting too much thought to it. It's doing brute force parallelism search isn't particularly cost effective. In fact, it's quite preclusive. And using Raytune really goes a long way in making sure that this is as efficient as it can get with fairly minimal effort. So in this manner, we're able to use the device in the loop while we tune for these multiple parameters to find the best model. So before we go to Q&A, I'll hand it back to Pang to say a few words, and then we'll head to Q&A.
Thank you, Saurabh. All right, so one last thing. So we published a blog post for this talk. It contains, the entire story of our building machine learning platform with Ray. And also one more thing, I want to acknowledge some of our scientist team who are here and who are not here. Maybe for the people who sit here, say hi to the rest of the audience. Thanks for your support and advice on building this platform. All right, and also we are hiring. So, cool. All right, so let's start the Q&A section. Questions?
I know Ray is introducing its own workflow, right? Are you looking or exploring into Ray workflow instead of Dagger or whatever, I forget that. Yeah.
Not right now. I think right now the focus was to make it more like agnostic to what's being used underneath, and just expose like a YAML-based, like no-code solution. So right now we're not using it. Right now we're in the mode where we're trying to add more and more capabilities to it. But yeah, at the end of the day, like the goal is at some point we're going to abstract away Dagster, and then we can just do a plug and play. Like if you want to use the workflow from Ray, you can use that, or you can use Dagster, you can use that, or Airflow, whatever.
Okay, thanks.
When you mentioned the models pushed to the camera, is it correct to think that it's a Ray actor and Ray task, and that's being deployed to the camera itself? So the camera is actually part of the Ray serving system?
So yes and no. In some cases, that can be the case if the camera is, if you can run Python on the camera and you can run Ray on the camera. In some of our cases, what we did was to keep the worker node isolated from the camera themselves and have a reservation system in between. So it's the worker node that runs the Ray actor, which just fans out to a camera that it's reserved for itself.
Is the worker node on the cloud or on the camera?
The worker node is on the cloud.
Okay, thank you.
Yeah, so there is several considerations here. So one is the camera's computation resource definitely, and also the actual runtime environment also matters, because we don't say, for some setup, maybe we can definitely run Ray on the camera, but that would deviate from the runtime pattern we run on the field in production. And we don't want that, because that may also impact some of the decisions we do quantization.
We have time for one last question.
Yeah, so not sure if I missed it, but were there any performance benefits for using Spark on Ray, or was it kind of just integrating everything into the Ray ecosystem? That was like the main reason.
Yeah, that's a good question. So far, we don't really see a big difference between running really open source Spark on, say, on top of Kubernetes or on top of Ray, because at the end of the day, Ray is just responsible for scheduling the actor. Everything is still using the native Spark framework to do the processing.
All right, that's all we have the time for, unfortunately. Thank you, folks. Just a reminder to please go to the Ray Summit app if you haven't downloaded already to leave feedback for this presentation. But we'll look forward to see you at the next talk.